Everyone, my name is Jorge Pilo, and today I would like to present our work entitled Electronic and Semiconductive Properties of Lithium, Indium, Chromium, Oxygen, and Lithium, Indium, Chromium, Sulfur double spinels, Structural, Magnetic, and Dynamical Insights from DFT+U. So the main objective of this work is to investigate how anion substitution, especially the substitution of oxygen by sulfur, affects the structural and electronic properties of these double spinel systems. So double spinel systems are particularly interesting because their physical properties can be strongly modified by relatively small changes in the chemical composition or crystal structure. So in this case, we focus on lithium, indium, chromium, oxygen, which I will refer to as LICO, and its sulfur substituted counterpart, that is the lithium, indium, chromium, sulfur, or LICS for short. So our calculation were performed with the density functional theory using the LSDA+U approximation. We use the Capelli-Alder-Perdue-Zunger chain correlation functional with a Hubbard U correction applied to the chromium D state. The calculations were performed using Siesta, while the phonon calculations were carried out in combination with the PhonoP softwares. So both systems were initially modeled considering the cubic F-43M structure, and we impose an antiferromagnetic configuration with the chromium atoms. So let me begin with the LICO system that is shown in the upper part of the poster, that is showing here at the video. So after structural optimization, LICO remained stable in cubic F-43M structure with an optimized lattice parameter of approximately 8.3 angstroms. So if we look at the electronic band structure showing here on the left part of the poster, the red solid lines correspond to the spin-up channel and the blue dashed line to the spin-down channel. So the calculation indicates a clear semiconducting behavior with a calculated band gap of approximately 1.623 electron volts. So next to the band structure, we shown the projected density of state, or PDOS, atomic PDOS, and this allows us to analyze the atomic contribution to the electronic state around the Fermi level and provide additional information about the electronic origin of the valence and conduction bands. So for LICO, we also calculate the phonon dispersion that is shown here. So this calculation gives us additional information about the dynamical behavior of the cubic oxide structure. And so our calculation in the LICO system provides the reference point for evaluating what happens when oxygen is replaced by sulfur atoms. So in the case of LICS, we have that we shown here, but initially we consider LICS in the same cubic F-43M symmetry, as LICO. However, during the structural optimization, we also obtained a tetragonal I 42M structure, while maintaining the antiferromagnetic configuration of the chromium atoms. So this structural modification is important because it also allows to separate two effects. So first, with the chemical effects associated with the replacing oxygen by sulfur, and second, the effect of the crystal symmetry on the electronic structure. So if we look first at the tetragonal LICS system that is shown here in the video, it is shown in the lower middle part of the poster, we obtain lattice parameters of approximately A equals B 7.1 angstrom and C equals to 10 angstroms. So its electronic band structure still with the semiconductor behavior, but the calculated band gap decreases to approximately 1.32 electron volts. So the character of this band gap is still being direct band gap because it's at gamma. So compared with the LICO system, replacing oxygen with sulfur and allowing the corresponding structural modification produces a significant reduction of the band gap. So if we consider the cubic LICS system, the lattice parameter increases significantly to approximate 10 angstroms, which is consistent with the larger size associated with the sulfur compared with the oxygen. So in the case of the band gap, the electronic band structure shows a smaller band gap than the cubic LICS system. So it is about 0.986 electron volts. So if we summarize these effects by chemical substitution, we have shown that the band gap reduces because of this chemical substitution of sulfur atoms of oxygen atoms by sulfur atoms. So if we indicate, well, we're not indicate, if we explore the magnetic configuration that is shown in the lower part of the poster, despite the structural and electronic modification, the system preserves the antiferromagnetic configuration between chromium atoms. So we have in this figure we shown the magnetic structure of the tetragonal in the case of the LICS system, and in the case of both LICO and LICS cubic system we shown the magnetic structure of F-42M structure. Red vector represent the chromium magnetic moment directions. So the calculated chromium magnetic moments are approximately positive or negative 3.05 Bohr magnetons for LICO system, cubic LICO system. In the case of cubic LICS system, we have a value of positive negative of 3.38 Bohr magnetons. And in the case of the tetragonal LICS system, we have a value of 3.39 Bohr magnetons. So the magnetic configuration are illustrated at the bottom of the poster like I shown in the video. So the sulfur substitution significantly affects the structural and electronic properties, while the antiferromagnetic characters associated with the chromium sublattice is maintaining. So this image is to summarize all the results of this work. And finally, overall, this structure suggests that chemical substitution provides a possible route for modifying the electronic band gap of this family of spinel system, preserving the magnetic characters. So maybe further calculation, particularly the analysis of the dynamical properties of the sulfur containing structures, will help us better understand the relative stability of the cubic and tetragonal phases and the mechanism associated with the structural transformation. So thank you very much for your attention, and I will be happy to answer any question at the IMRC Congress online. So thank you very much.